Okay, up to this point, we've gone through these formulas for z-scores. Z equals x minus mu all over sigma. That's for one item. It's for when you know the mean and you know the standard deviation. Then you have zx bar, which is for groups of items. 5 items, 10 items, 12 items, 42 items. The average of your sample minus the average overall over the standard deviation divided by square root of n. Additionally, you have t equals x bar minus mu over s divided by square root of n, but that's only if you have smaller samples or you do not have the population standard deviation. Additionally, we did the confidence intervals, and with confidence intervals, we come up with this big equation here, which could also, of course, be written as x bar plus or minus the margin of error, or x bar plus or minus z s over square root n. All three of these mean the same thing. However, that's if you have an average, a height, a length, a width, a years, or something like that. On the other hand, what if you had a percentage or a proportion, for example, of 53 households? Out of 53 households, 93% of respondents had a DVD player. So, if we wanted to find what are the chances that in a certain town the probability that proportion is greater than 94% having a DVD player, we would need to do a z-score, much like we did over here. We're going to need a different formula, however. Z, because it's still a z-score, is going to equal p hat minus p all over the square root of pq divided by n. Now, let's talk about what each of these things is. P hat is your sample P, your sample proportion probability percent. P is the population proportion. Q is the complement of P. So if this is 93%, as you see here, 93%, this is going to be 7%. And finally, of course, N is the number of households. Now, let's actually go ahead and attempt to use that information on a problem. So we want to find a z-score here. Now, to do that, we would say z equals, now, the proportion we want to find is 94%, but I can't put percents in math problems, so we change it to 0.94 minus the population proportion, which is 0.93, all over. Now, you'll notice we don't have a standard deviation. There is no standard deviation listed on this problem. So what we need to do is we need to find the standard deviation. And that standard deviation is going to be P times Q over N, and we're going to take the square root of the whole thing. 1 second. Had a camera freeze, all we had was that sigma is equal to the square root of P times Q all over N. So in our case, P, our population proportion, because that doesn't have a little hat over it, the little hat means sample, 0.93 times 0.07, don't forget 0.07, all over N, and we had 53 households. So here we go. I'll do a couple calculations and I'll be right back. Okay, by doing a few calculations, we come up with 0.94 minus 0.93 is 0.01. I do all of this as one unit, put the number right here. When I do that division, I get a z-score of 0.285. Now, does that make sense? Well, 0.94 is above average, even though it's not very much above average, so that seems to make sense. Our original question was, what are the chances that p hat is greater than 0.94? So I'm going to go to my probability distribution calculator, and I'm going to say, well, 53 households is plenty, and I have a z-score of 0.285. Calculate that. I want greater than, again, I want greater than, so we're going to take the area to the right. So the probability that p hat is greater than 0.94 is 0.388. So the chances that out of 53 households that 94% rather than 93%, 94% or greater is about 39%. That's the chances. You'll notice it's the same z-score stuff, it's just with p-values using this formula right here. Now, the same thing also applies when we start talking about confidence intervals. So on a confidence interval, instead of x bar minus z alpha, etc., we get the following. P hat minus z, and you'll notice for this we need our square root again, so we have square root pq over n, but this one's p hat q hat less than or equal to p less than or equal to p hat plus z square root p hat q hat over n. This is the one time that this is a little bit different, and that's because with this, we don't have to have a true population number. You'll notice from the sample, from the sample, from the sample, from the sample. All this is from the sample. So let's see what kind of confidence interval I should be guessing at instead of trying to just shoot for 94%. So let's see what we come up with here on the next example. If I surveyed 110 households, and I found in my sample that p hat equals 0.91, or 91% of households have a DVD player, what range could I be 95% confident in if I were to do another sample? So I want to be 95% confident. So I'm going to say p hat 0.91 minus z. Well, I have more than enough households, so I could simply go to my probability distribution calculator, type in 0.95, and it's going to come up with 1.96 times, now p hat 0.91 times q 0.09, because remember those two have to make 1, all over 110. It's less than or equal to p less than or equal to 0.91 plus 1.96 square root of 0.91, 0.09, all over 110. I'll do the calculation. I'll be right back. Okay, by plugging in this information into a calculator, I find my margin of error is 0.053, or about 5%. So I have p hat minus that, and I have p hat plus the margin of error, and I come up with 0.937, 0.9037. Nope, pause. Let me do this with a calculator. Here we go. 0.91 minus 0.053. There we go. 0.857 less than or equal to 91, so that's 0.963. So I could be 95% confident that it would be somewhere between 86% and 96.3%. So that's my range. That's confidence intervals for proportions. That's z-scores for proportions. And that generally finishes what we're going to be doing for the bulk of the z-score portion, meaning we should be coming up ready for a test coming up probably a week or so after we get back. So with that, take a look at all of the various review sheets, all the various assignments, and the number of examples that I have. I've labeled them confidence interval examples, z-score example, etc. Look through them, do some problems, then when we come back together, we'll put all this stuff together.